Hi, everyone. Thank you for joining us for today's Fundamentals of Battery Testing webinar. I am Meredith Kenton, MEGGER's Digital Marketing Specialist. If you have any questions about webinars in general or this webinar, feel free to reach out to me via email or phone. If you have questions, application questions about what you're learning today, I ask that you submit your questions on the panel on the right-hand side of your screen. It should look just like this one. At the end of the presentation, I will ask Andy as many questions as we can get through. And if your question doesn't get an answer, don't worry, we will make sure we get you an answer via email if we run out of time. And then on that note, I would like to introduce you to today's presenter, Andy Sagl. He is our product manager for power quality and battery testing at MEGGER. I always like to mention if you have specific application questions about battery testing, please reach out to him via email instead of me. And on that note, I will pass it over to Andy.
Hello, everyone. And today we are going to cover the fundamentals of battery maintenance and battery testing. Our agenda, what we're going to cover here is we're going to cover different battery types. There are various applications, the failure modes they can experience, the different test methods that can be used. We're going to discuss ohmic testing and the pitfalls that you can have when doing testing. And then we're going to cover some of the maintenance schedules. So let's first jump into the battery types. On a very broad scale, there are two types of batteries. You have the primary cells and secondary cells. The primary cells, these are the things we're all used to. These are our energizers, our Duracell. These are our disposable alkaline batteries, as well as lithium batteries. And when they die, we throw them away. Secondary cells, now these consist of our lead acid batteries, NiCad, as well as lithium ion batteries. And these cells are our rechargeable cells. And when they're manufactured, they don't have a charge. They require a secondary process to charge them up, hence the name secondary cells. And of these types of batteries, there are several different types. We have, what we're going to cover is we're going to talk about the lead acid, the NiCad, as well as the lithium ion batteries. Now, lead acid batteries, these can also be broken down into cyclic batteries and standby batteries. The cyclic batteries, these are the ones that are designed specifically to cycle, commonly used in things like golf carts and forklifts. Where standby batteries, these are designed more to stay on float. And these are what are going to be used more in substation, telecommunications, as well as data centers and UPSs. Now, we break these down further. Lead acid, they can come in several different chemistries, but regardless of the chemistry, they'll all either be flooded cells or sealed cells. Now, flooded cells, or VLA, vented lead acid, these are the type of batteries. They're big. They're usually clear so we can see inside of them, but not all of them. And they have a lot of electrolyte in them. And we have to periodically add distilled water because as these batteries discharge, they do vent hydrogen gas. That hydrogen comes out of the water in the electrolyte, hence why we have to add distilled water periodically. Now, one of the pros of these type of batteries is that these batteries can be very long life because of all the electrolyte in them. We can get lifespans of 20 to 25 years out of these type of batteries. Another pro is that when they fail, they tend to fail in what's referred to as a shorted mode. It does not mean they're shorted, but what it does mean is you can typically still get current through them, so you can use series strings in critical applications. Some of the cons, well, one of the biggest cons is they vent hydrogen. And when people hear that, they usually think the first thing that comes to mind is images of the Hindenburg going up. But it really, when we think about it, hydrogen is the lightest gas. It's the first element on the periodic table, which means it rises very quickly and disperses quickly. So really, we just want to make sure we have adequate ventilation. We don't want to put these type of batteries in small areas that are unventilated, because then you can get a hydrogen buildup. Another con of these batteries is they are heavy. The steel type of batteries, or commonly referred to as maintenance-free, are valve-regulated lead-acid batteries, or VRLA. The maintenance-free portion of it refers to the fact that you can't add distilled water to it. In reality, they actually sort of require more maintenance because of the fact you can't add water to them. And I'll get into that a little bit later on. But these type of batteries, when they discharge, they also create hydrogen and oxygen. However, in normal operating conditions, these aren't vented. They are sent over to the negative plate where a recombination effect takes place. They steal electrons off that plate to reform the water in the electrolyte, so you don't have to add water. One of the pros of these type of batteries is they're relatively inexpensive. Okay? They're some of the cheapest batteries you can use. They are commodity items. Some of the cons is these type of batteries, because they work within electrolyte-starved mode, they don't have a lot of electrolyte, they tend to dry out and the separators shrink and can pull away from the plates. This makes them fail in what's referred to as an open mode. Now, it doesn't mean they're open. It just means that current cannot readily pass through them. So if these are to be used in critical applications, it's recommended to use parallel strings so that if one battery fails, you can still get current through the parallel string. They also, because of the small amounts of electrolyte in them, have a limited lifespan. Typically, you get 5 to 8 years, and there are some that are longer life than that, but that is a typical lifespan. And there are some out there that will last you 2 years. That their quality is questionable. The other thing is these type of batteries should stay in temperature-controlled environments because they do dry out, and higher temperatures will make that happen quicker. NiCad batteries, nickel cadmium. These are a little bit different. Instead of in lead-acid batteries, you have an acidic electrolyte. In these type of batteries, NiCads, you have an alkaline electrolyte, a potassium hydroxide. This actually changes the discharge profile of these batteries. In lead-acid batteries, as they discharge, the voltage drops slowly as the impedance rises and the capacity drops. In NiCad batteries, the voltage will remain fairly constant as well as the impedance as the capacity is dropping. It's only toward the end of their capacity will you actually see the voltage drop off and the impedance rise. Some of the pros of NiCad batteries is that they have a better temperature performance than lead acid. Now, this doesn't mean they're not affected by temperature. It just means that they have a better performance characteristics at high-end temperatures. So if you're in areas where you have non-temperature control and it can get warmer, you may want to investigate these type of batteries. They also have a fairly long lifespan. They can be 10 to 20 years. Some of the cons is, one, they're more expensive, and two, they are prone to dendrite buildup and can fail suddenly. And we're going to get into that a little bit more when we cover the failure modes. Lithium-ion batteries. Now, lithium-ion batteries, this is actually a family of batteries. It's all different chemistries, and they have different characteristics. They are designed for different applications, and different chemistries will give you different trade-offs. So really, you want to look at your application and make sure you choose the proper battery for that application. And actually, let's go into that now, the battery applications. Okay, batteries, they are not designed equally. Different applications require different designs. There are various things we want to look at, such as plate surface area, battery chemistry, and right now, let's just look at the plate surface area. The more surface area I have, the more charge I can have on that battery, the more capacity it will have, and the more current it can deliver. So when I have these applications that require a lot of capacity, I'm going to end up having larger cells. Okay. Now, batteries also in the cyclic applications, these will actually want to have thicker plates in them. Why is that? Well, when I'm discharging and recharging, I'm producing heat. So the thicker plates allow me to deal with that heating and cooling effect much better. So in cyclic applications, I want to use thicker plates. And now I also have different chemistries I can use. Some of the common chemistries out there today is lead antimony and lead calcium. You can also have pure lead, and there's also lead selenium. Now, lead antimony batteries, originally when lead, let me first start by saying originally lead acid batteries were always pure lead. And one of the problems you have with that now, pure lead batteries can have some of the longest lifespans. However, one of the problems you run into it is that they don't handle heating effects very well. Lead is a soft metal. And also you couldn't build them up very high. So we started making lead antimony batteries. And basically the batteries will have an antimony grid in them. This makes them stronger. I can make them larger, and they deal with heating effects better. So they're very good in cyclic applications. However, they're not outstanding for floating applications, for standby applications where they remain on float for long periods of time. This is because the antimony can dissolve into the electrolyte. It's referred to as antimony poisoning. And anyone that has had batteries with high antimony content on float will notice that their float current will go up over time as the antimony poisoning increases. This is where lead calcium batteries were developed. And the lead calcium batteries, the benefit of those is that they don't draw as much float current and they don't suffer from antimony poisoning. So they're very good in standby applications. However, they're not as good in cyclic applications because they don't have as much resilience to the repeated heating of the charging and discharging cycles. So in cyclic applications, such as forklifts and golf carts and things of that nature, we really want to look for something that has a good lead antimony design. We want thicker plates. They're stronger, and these will be typical in deep discharge batteries. And in stationary batteries, we want to have more of our lead calcium, lead selenium, which is basically a lead antimony with very small antimony content in it. These are very good in your standby applications, such as substation, telecom, and data centers. Now, there's another type of battery, too, that I haven't touched on yet, the SLI batteries, starting, lighting, and ignition batteries. Now, these are typically the type of batteries that are used to start a car engine. These are designed much differently, too. If we think about what a car engine has to do to start, it has to draw a lot of current very quickly. So these type of batteries have a lot of very thin plates to maximize surface area that are very close together. They have very small separators in between them. They're very thin, and they're under compression. These are specifically designed to supply high levels of current for very small periods of time. And they need to be recharged right away. They're not meant for deep discharge. This is why cars have alternators in them. As soon as they're started, the alternator has to recharge that battery. And as we get into failure modes, you'll see why. So, NiCad batteries. NiCad batteries have a higher energy density than lead acid. So where you have limited space, these are a good choice. And they also are very tolerant of deep discharge. Now, as I said, lead acid batteries and lithium ion, if they get discharged too low, they can be damaged. NiCad batteries can handle being discharged almost all the way down to zero. You just want to be careful you don't reverse the polarity of them. And they're very good at wide temperature ranges. They can be used to up to 70 C. That doesn't mean temperature doesn't affect them. It does. It's just they're more tolerant of it. This is one of the reasons that in a lot of handheld tools, you'll see NiCad batteries used because these can sit on the shelf for a long period of time. I know my portable drill, I'll leave that on the shelf for months on end, not touch it. And when I pull it out, my batteries will be real low. If I was to use a lead acid or a lithium ion on there, and I left it on where it got down to near zero, they would no longer work. A NiCad battery can actually do that. Now, lithium-ion batteries. Now, lithium-ion batteries, as I said, come in many different chemistries, and they also come in different configurations. You can have cylinder packs, prismatic, or pouches. And cylinders are what we're seeing in the top right image there. You have multiple cylinders in series and parallel to create the proper capacity that's required as well as voltage. Prismatic batteries are a similar concept, and they'll be stacked up in the battery itself, so you'll have multiple ones in there, and same with the pouches. So in general, lithium-ion batteries will consist of smaller cells inside each of these packs, and they can be in series and parallel both. So one of the things that's required in them is, you'll see in that top picture, there is a electronic circuit board in there. This is called the battery management system, the BMS. In lithium-ion batteries, it's critical that the cells within them remain balanced. So this is what the function of that built-in battery management system is. That's just the function of the BMS, to keep those cells balanced. It also monitors the charge and discharge rate of the batteries to ensure they don't charge too quickly or discharge too quickly. Okay, so when we're looking at lithium-ion batteries, we want to make sure not only we select the right chemistry, but we also want to make sure that our charging methods and discharging methods meet the requirements of those batteries, and those you'd want to check with the battery manufacturer. So let's go into some of the failure modes along the different batteries. Positive grid corrosion. Now, this is a normal failure mode that's going to occur in lead-acid batteries. This occurs over time. As the batteries age, the lead alloy turns into a lead oxide. And one of the things you'll notice is that the lead oxide is a larger crystalline structure. So one of the things you might notice is the plates in these batteries will actually grow. So if you have a VLA battery, vented lead acid, flooded cell, that's clear, you might notice there's a gap at the bottom space. This allows for plate growth. And basically, as I said, grid corrosion is a natural thing that happens over age as things oxidize. However, the process can be accelerated. What accelerates this? Heat. So what happens to molecules when you heat them up? They're going to move faster. This will accelerate chemical reactions, hence accelerating corrosion. So what in batteries causes heating effects? Well, overcharging is number one. Number two, excessive cycling, and excessive temperature if they're in very hot environments. And as the plates corrode, the plates are losing active surface area. That lead alloy is turning to a lead oxide. You're losing active surface area. As you lose active surface area, the impedance increases in them as the capacity decreases. Sulfation. This also occurs in lead-acid batteries, and it is natural. This happens as the battery discharges. As the battery discharges, the active material in plates turns into a lead sulfate. Okay. As you recharge them, this process reverses itself. Now, the problem can occur is what happens when we're undercharging the batteries. If we don't fully charge the batteries, if they remain undercharged, then they're going to be partially sulfated. And the problem is, the longer they remain sulfated, the harder it is to reverse that process. Now, some of you may have heard of equalization charging or boost charging. This is where we set the charger voltage to a higher value than the normal float voltage for a given amount of time. The purpose of this is to try to break down the sulfation crystals on the plate. And in this way, we regain some of our capacity. This is what an equalization charge is doing. The thing is the longer the batteries remain sulfated, the harder it is to reverse that. And at some point, equalization will no longer work. And again, as the plates sulfate, they're losing active material on them. So we're going to see the internal impedance of the battery rise as the capacity drops. Shorts. Now, in batteries, there are basically two types of shorts we can get. We can get what's referred to as hard shorts and soft shorts. Hard shorts, these are typically manufacturing issues that are caused by paste lumps. And the paste lumps will push through the separator and short out the plates. So if any of you have ever put in new batteries and seen a week or so, suddenly they failed, most likely it's due to a paste lump that has occurred that has caused the voltage to drop on them, and the impedance also will go down. Now, we also have soft shorts. Now, soft shorts occur due to deep discharging. On lead-acid batteries, when we discharge them, they're only really designed to be discharged down to about the 80th percentile in general, 80 percentile of voltage. When we go lower than that, what ends up happening is the specific gravity of the electrolyte will approach 1.0. This is the specific gravity of water. It's also referred to as watering the battery. When this occurs, the lead on the plates will begin to dissolve into that electrolyte, and it can get trapped in the separators. And this can create a whole bunch of micro shorts in there. This is where I go back to the car battery. As mentioned, the SLI battery used to start your car. This type of battery is not designed for deep discharges. When it gets discharged, the lead will begin to dissolve into that electrolyte, and it will get trapped in the separators. And in this design, the separators are thin, okay, because these batteries are designed to supply maximum current. So when we have anyone that's ever had a car battery die, you'll notice you'll jump it, you'll get to where you're going, and then you'll leave it like that. Next thing you know, it dies again very quickly. You jump it, charge it back up, and then it dies even quicker. Every time that it dies, what's happening is more lead is leaching into the electrolyte and getting trapped in the separators. So you're creating more micro shorts in the battery. That increases the internal discharge of the battery. Its self-discharge rate increases because its resistance is going down. So this is why they will fail faster and faster. In fact, we hear all the time, as they get shorts, they get hotter and hotter, okay, because you have more self-discharge current going through them. We all hear about lithium-ion batteries. Every time there's a fire with a lithium-ion battery, it's reported. But in truth be said, the batteries that have the most fires are car batteries, because people don't replace them when they die. They just keep trying to use them. So really, if you do have a car battery and it drops, get it jumped, get to where you're going, but replace the battery. And now this, like I said, shorts, they're not just, I'm talking about car batteries here, but they're not specific to that. Any type of lead acid battery, you go too low in voltage, you'll get a dendrite buildup that can pierce the separator and create shorts. In these cases, you'll see the voltage go down and the impedance drop as well. Dry out, or loss of compression. Now, this is specific to VRLA batteries, sealed batteries, or what we call the maintenance-free. As I said before, as these batteries discharge, they do create hydrogen, and oxygen gets routed over to the negative plate, and a recombination effect occurs to recreate your water in your electrolyte, so you don't add water to them. The issue you run into, though, is no chemical process is 100% efficient. So these batteries do dry out slowly over time. Now, this is why they have a limited lifespan too, by the way. Now, what can accelerate that dry out? Heat. Heat can accelerate it. So what can create the heat in the battery? Overcycling, overcharging, very high ambient temperatures. And now think about it. As the battery dries out, there's less electrolyte in it, it's actually going to draw more flow current. As it draws more flow current, it's going to run hotter, which will make it dry out faster, which will cause it to draw more flow current and run hotter and dry out faster. You can see how this can become a cycle. And in fact, at some point, it becomes a self-sustaining reaction that can lead to a thermal runaway. And in this case, when you have a thermal runaway, what will happen is the battery will only fail on one of several modes. It will either catch on fire, melt, or explode. So this is one of the conditions we want to avoid. So how do we avoid this? Well, one of the easiest things to do is if you're using VRLA batteries, you want to use a temperature compensated charger. These type of chargers will monitor the temperature and make sure that you do not exceed your flow current values. And the other thing you want to do is monitor your flow current. You want to make sure that's part of your maintenance routine. And if you see flow current going up over time, this is a flag that we want to investigate. Negative plate depolarization. This also occurs in VRLA batteries, and this is due to the recombination effect. And this occurs when you charge them too quickly. When they're charged too quickly, the negative plate can become depolarized. Now, in order to measure this effect, there's several different types of tests you can do. You could do a DC resistance test or an AC impedance test. However, a DC resistance test will not pick up this failure mode. That is because when we look at a battery is not a resistor. It has capacitive properties to it. A battery has an electrolyte, which is a fluid, and has plates, which are solids. Whenever a fluid meets a solid, you've got what's referred to as a double layer capacitance. It basically forms a capacitor, and electrons build on both sides. And when the plate depolarizes, you're going to see that as a change in the capacitive properties of the battery, not the resistive ones. So whenever we use VRLA batteries, because of this type of failure mode, we always want to do an AC style test on them so that this failure mode can be picked up. Carbonation. This is applicable to NiCad batteries. And what happens here is the potassium hydroxide electrolyte will enter into a chemical combination with atmospheric carbon dioxide, and it forms potassium carbonate. Potassium carbonate has a higher impedance, so it's resistive to current flow. So what it will do is it will decrease the amount of capacity or the amount of current the battery can deliver. And this will be seen over time as a rise in impedance on the NiCad battery. Now, this type of failure, it can be accelerated when you're in hot environments. Also, if you're in environments that are rich in CO2, if you have engine exhausts or anything like that, that can accelerate this type of failure mode. However, this failure mode can be reversed. If you have flooded NiCad batteries, you can change the electrolyte to actually reverse this condition should you see it happening. Dendrite formation. This is also common in NiCad batteries. On the right there is an image from a NASA study, and you can see the dendrite formations occurring on the cadmium. And cadmiums are prone to dendrite formation. And what will happen as they grow, they can pierce the separator and short out the plates. So we'll notice NiCad batteries do fail shorted. And periodically, what will happen is if you find you're having problems with NiCad batteries, the manufacturer may tell you to bring the battery voltage all the way down to near zero and then recharge it. And basically reconditioning the battery. When we do that, what we're actually doing is during that recharge process, we're creating a lot of heat in the battery and we're burning away the dendrites to regain that capacity. However, although we can burn the dendrites away, the damage to the separators where the dendrites grew through is permanent. So basically, they will grow through there. So this is a process that will have to be continued. Now, lithium-ion batteries. Now, as these age, they have what's called a solid electrolyte interface layer. They need this to actually operate, but as they age, this layer builds up. As it builds up, the impedance of the battery increases, decreasing the battery capacity. It's also referred to as capacitive fading. This is why lithium-ion batteries do need to be derated over time, because over time, this layer gets thicker. So right here, we can actually see the correlation between capacity and impedance on the lithium-ion batteries. So as the impedance goes up, the capacity goes down. Another failure mode you can get in lithium-ion batteries is called lithium plating. This occurs when they're charged too quickly. Now, in a lithium-ion battery, lithium ions are transferred between the plates. Now, the anodes can only accept the ions at a maximum rate, or a maximum rate of intercalation. So when we exceed this maximum rate, what will happen is the lithium will plate on the surface, creating dendrites that can short through the separators. This is why they have the BMS system, to make sure that this doesn't occur. It monitors the maximum rate of the charge. This is also very temperature dependent. Now, before I mentioned as batteries heat up, what happens? The molecules move faster, so reactions increase. What happens when they're cold? Well, when they're cold, what will happen is that the rate, the molecules move slower. So your maximum rate of intercalation decreases. So the BMS within the system has to monitor that temperature and adjust the charge rates properly to verify that they do not have lithium plating that can occur, because this can lead to critical failures. Okay, they can lead to runaway failures. And loose connections. When we talk about battery maintenance, everyone always focuses on battery. The straps are just as important. You can think of the battery, the straps between the batteries and a string as little tiny resistors. Each one has a voltage drop across it. So now, what happens if I have a bad connection? The torque gets loosened up, or I have some corrosion occurring on them. What will happen is the resistance on them will go up. So the voltage drop across them goes up. So what ends up happening is this charge on one side of the battery, on one side of the string, is lower than the other side. So those batteries won't get fully charged. So what will happen to them? Well, if they're not fully charged, they're going to remain partially sulfated. The longer they stay that way, the harder it is to reverse the process. So whenever we maintain a battery string, not only do we want to test the batteries, we want to make sure the straps are good, because these things, the straps are affected by vibration. They're affected by expansion and contraction from heating and cooling. They're affected from moisture, and also contaminants can get in. So let's talk about the different battery testing methods. One thing to understand is that there is no single test that's going to tell you the whole story. What we want to do is create a maintenance routine applicable to the type of battery that you have that will allow you to determine the condition the battery is in at present and where it's heading to. And this can consist of many different types of tests: visual inspection, float voltage, float current, ripple current, specific gravity, temperature testing, discharge testing, ohmic testing, and of course strap or intercell testing. Visual inspection, very simple to do, but it's something we really do need to do. We want to check things like electrolyte levels on flooded cells. Make sure it's within the proper limits. We don't want it to overfill it or underfill it. We want to check the battery for cracks, leaks, or deformations. If we see a battery that's bulging, we're pretty well done at that point. You want to replace that battery, because If it's bulging, what's going to happen next? Well, you're going to end up getting a crack. You're going to get leaks that occur, and the electrolyte is acidic. We don't want that leaking around. It's a hazard. Check for strap corrosion. If we see strap corrosion, clean it. Verify there are no ground faults in the system. Verify the ventilation is working properly. Room cleanliness. And verify the battery rack hasn't decayed. And it's also recommended to always record this information because you want to see if there's patterns occurring. Float voltages. Now, batteries can be sources or loads in a string. If I have a battery that has a low voltage next to one that has a higher voltage, where's the current going to flow? It's going to go from the higher to the lower. So the low battery will act as a load on the other battery. So in general, your battery string is only going to be as good as the weakest battery in it. So we want to measure the float voltage across each cell. And we do this during float conditions, and we're going to compare it to the battery manufacturer's recommendations. Now, one pitfall you can run into here is using a digital multimeter to do this. A digital multimeter has a very high impedance to it. So even batteries that have a low capacity could read good on a DMM. So you really sort of want to use a battery tester on this, or something that has a little bit of a load that when you put it on there, it will try to draw some current from the battery. Otherwise, you may get false readings. Now, what happens when we have a low float voltage? Well, that means the battery is not fully charged and the plates are partially sulfated. High float voltages mean you're overcharging it and you're heating the battery up. Float current. We want to check that float current. Remember what we said before. If we see float current rising over time, that can be an issue. We want to take the measurement at some place in the string. Any location is fine because Kirchhoff's law says the current's going to be equal throughout that string. So we're going to look at that. And most chargers today will have the float current right on them. And we basically want to monitor this and see, is it rising over time? If it is, we want to investigate. Now, we might find that we have flooded lead antimony batteries, and maybe that means that's a sign it could be antimony poisoning. Maybe next time we want to go to lead calcium. If they're VRLA batteries, we want to check, do we have a temperature compensated charger? If not, and we see that float current going up, that's something we want to look into because that could end up leading to a thermal runaway if it's not corrected. Ripple current. Now, float current is the DC current going through the string. Ripple current is the AC current going through the string. Now, why would there be AC current? Well, we have a charger on the system. Those charges are going to convert AC to DC. But that process is not 100% efficient. You're always going to have some ripple. Typically, it's very small. IEEE recommends that the ripple current not exceed 5 amps for every 100 amp hour capacity of the battery. So in general, unless the charger has an actual open rectifier in it, it really is not going to pass that. But that's something we want to check. If we do see high ripple, that's a sign that we do have a problem with the charger. Or it could be coming from the load as well. It's not uncommon to have high ripple levels in UPS systems. The other thing that's important about ripple is the frequency. Now, typically these are lower frequency values in ripple. And most batteries, high frequency really doesn't bother them, but when you get into low frequency where it could be pushing the float voltage up and down below and above the actual float voltage recommendations, that can cause additional heating in the batteries. Now, I said that higher frequencies aren't really a big problem for the batteries. However, one thing to note is that in lithium-ion batteries, some BMS has been reported to fail due to medium frequency harmonics. In the 10 kilohertz, 15 kilohertz range has caused some BMS failures. So although the batteries are not susceptible as to the higher frequencies, the battery monitoring, battery management systems may be. Specific gravity. This here is a measurement of the density of the electrolyte as compared to water. So it basically is looking at how much sulfate is in the electrolyte of the lead acid battery. This is really what this is really doing is checking the state of charge of the battery. So if you have and a NiCad battery, it doesn't tell you anything. If you have a lead acid battery, lead calcium, it's not going to tell you much. The only place this is really applicable is if you have a flooded lead antimony battery. In those cases, this will help you identify if there is antimony poisoning occurring. But other than this, as long as you're measuring the float current, this test will be sort of redundant. Temperature. Okay, there is something called the Arrhenius life stress model. I'm not sure if I'm pronouncing that correctly. But basically, it has to do with any chemical reaction. As temperature increases, molecules move faster, chemical reactions happen faster. And all batteries are chemical devices. And in general, for every rise in temperature of 10 degrees C on that battery, you're halving the life of it. So this is why we want to keep these batteries in more temperature-controlled environments. So regardless of the type of battery, temperature will have an impact on it. And certain batteries like VRLA should really be kept in temperature-controlled environments because they work in an electrolyte-starved mode. Discharge testing. Now, discharge testing is the only test that will actually measure the actual capacity of the battery. And it's recommended to be performed every quarter of the lifespan of the battery. So if I have a battery that has a 20-year lifespan, I want to be doing this every 5 years. If I have a battery with a 10-year lifespan, I want to do it every half years. Now, this will tell you how much capacity you have at that point, but one thing to keep in mind is that batteries can fail within this time span. So discharge testing is just part of a maintenance routine. And when discharge testing is done, you first want to run a battery test, run a ohmic test through the battery string, equalize it, let it cool. You would perform the discharge test. And when this is done on critical systems, you need to bring in another battery strap because you're going to be draining this one down. So you want to bring in another battery string and connect it. So this is a long test to do. This is why it's only done every quarter of the lifespan of the battery. Ohmic testing. Ohmic testing is either going to draw or it is going to inject a current through the battery and then look at the voltage drop across the battery. In this way, it will determine the resistance or impedance of the battery. As the battery ages, its chemistry changes. And so its ohmic value will change. And intercell resistance, this is one that we talked about previously. This is a critical one to do. And we want to always try to do the measurements across on the posts. Why do we want to do them on the posts? Because if we do them on the post, we're going to not only include the battery strap measurement, but the connection between the battery and the strap, also called the terminal resistance. So this is why we want to take it off that post. This way, we're looking at the terminal resistance, the connection from the terminal to the strap, as well as that strap connection. So we get everything all in one. Typically, IEEE will tell you if the strap impedance or resistance has changed by 20%, you should really take them apart, clean them, put them back together, and retorque them. So let's talk about some ohmic testing here. There's basically 3 types of ohmic tests. You have resistive, conductance, and impedance testing. Now, they all have their pros and cons. Okay, resistance testing. One of the pros of resistance testing is it tests with high current. But one of the cons is it also pulls that current from the battery. So it pulls a lot of resistance from the battery, and it starts discharging the battery. Now, the problem is, what happens if you were to slip on this reading and you have to retake it? You cannot retake it immediately. You have to wait for that battery to charge back up before you get the same reading. The other con to it is that a battery is not a resistor, as I discussed earlier. It does have a capacitive double layer in it, and this type of test will not measure the capacitive properties of the battery. Conductance testing. Now, conductance is actually the reciprocal of resistance. However, What these manufacturers are actually doing is admittance. They're doing the reciprocal of impedance. So basically taking an impedance value and dividing it into 1. Now, the pro is that it will detect capacitive changes in the battery, and it doesn't pull current from the battery, it injects current through the battery. The cons, well, one, these tests are done at very low current levels. And you can see right here, that little green square wave, modulated square wave, that's the test current that's used on it. And that's going to limit the resolution you can get out of it. So it's not very good on larger cells. It's typically designed for VRLA batteries. The other thing is their test frequency will typically operate in the 1 kilohertz range. This is in the noise range. So when used on something like a UPS system, you may find you have to take the UPS system offline in order to do the testing because the noise will just swamp it. We've also gotten some reports from the field that on some types of batteries, the algorithm's not always correct. As I said, this is really designed for VRLA batteries. Impedance testing. Impedance testing is a 4-lead Kelvin measurement. It's going to inject current through the cell, an AC current, and measure the voltage drop across that cell. And then it will, by having those two values, it can calculate the impedance. Pros, it will detect capacitive changes. It doesn't pull current from the battery, and it doesn't use any algorithms. Okay. Things to note on this. Some of the cons can be, one, depending on the testers, you can get ones that are low current or high current. Low current ones are not adequate for doing large cells. So you want to look at how large the cell is versus how much current you're going to use to do the test. Also, they can operate at various frequencies. If you have ones that are putting out 1 kilohertz and you're on something like a UPS system, you could have problems with noise damping it out. So you may want to go more toward low frequency instead of higher frequencies. Now, one of the important things to understand about ohmic testing is it's not an absolute test. This is not going to tell you this battery is good, this one's bad. It's going to be a relative test. You're looking at how much the battery has changed from other factors, such as other batteries in the string or a baseline value or the value when you first started testing. And we're going to basically see how much it's changed and get an idea of how it's aged. And in order to do this, there's several things we have to make sure of. One, the battery strings need to be fully charged. You want to make sure you use the same make and model instrument. If you do change the make and model, you need to actually change your baseline reference value because you could be operating at a different frequency. You want to use the same probe type. If you change from one type of probe to another, it could affect the readings. And you always want to make sure you take the measurements at the same point on the batteries. And posts are the preferable location. But if one person does posts and someone else takes it off the hardware, you are going to get some difference in readings. Now let's talk about some of the pitfalls we can get into. One is batteries are low impedance devices. The bigger the battery, the larger the plate surface area, the lower the impedance. So I don't want to be testing a battery that is 100 milliohm with a test current of only 100 milliamps, because then the voltage drop is only going to be 10 millivolts. So that can get swamped due to noise and skew the results. So if the test current is more around 10 amps, the voltage drop is 1 volt. That's 100 times higher. So it's going to avoid a lot of false results due to noise. The other issue is strap resistance is in microohms. I can't test strap resistance with 100 milliamps. This is why when I try to measure low values in the microohms, I don't use an ohm meter. I use a low resistance ohm meter, a DLRO, because it has higher currents. So these are some of the things to watch out for when you are looking at getting battery test equipment. Watch that test current. And as I said, the straps, now they're low resistance. Now you may choose to use a low resistance ohm meter, DLRO, to test a strap. However, keep in mind, when I'm testing a strap on a battery, I already have a DC current going through it. Low resistance ohm meters use DC current to do the test. So if I test it in one direction and then test it in another direction, I'm going to get 2 different readings. So what I want to do is test it in each direction and take the average of the 2. Some DLROs actually have that function built into them. So it's just something to keep in mind. The other thing is that whenever I'm using duplex leads, and what I mean by duplex leads is I have a probe with 2 pins on each one. One injects current and one measures voltage. Whenever I'm doing this, it's going to be a relative measurement, not absolute. This is because I don't have uniform current density going through the strap. It takes time for the current to expand and become uniform. So if I was to use a different set of probes where the tips were further apart, I'm going to get a different reading. Now, if I have a system that injects current through the entire string, and I'm taking measurements on the posts, then the readings will be absolute because I have a uniform current density going through the entire string. So basically, if I'm going to be using this type of setup with duplex leads, I want to always make sure I'm comparing it based on 20% of the previous reading or 20% of the string average. Okay. If I'm injecting current through the entire string, I can really go on absolute values. Stainless steel hardware. This is something we want to watch out for. This is one of the reasons we want to take measurements off the post. You use stainless steel hardware. They tend to have a higher impedance to them, so they can skew your readings. So if I have a duplex system, note, I'm going to be injecting current directly through that stainless steel, which means that I'm going to be including those voltage drops in the reading. If I have a system that is injecting current through the entire string, then I'm not having to deal with that hardware. It goes actually right through from the strap to the terminal, right through the battery. So I will be able to actually get better measurements with that. And parallel strings. When I have a series string and I got to inject current through a battery, look, I only have one path it goes through to the cell I'm measuring. What happens when I have a parallel string? Now I have escape current going through a parallel path. I have another path for it to go, but the tester only sees the actual total current coming out of it. So the problem is you're not going to get a real reading on any of the batteries. This is why IEEE recommends segmenting the strings so that you can get true readings. Because if you have one battery that goes bad, it's going to change the reading on every battery in the string because it will change the current going through them. So you'll never isolate that battery without segmenting the string. In these cases, you can use a extra CT, and the CT is put on the parallel string to measure the escape current going through the string. This way, I now know the total current and the escape current. I can subtract them and come up with the actual test current. So I get real readings on each battery, so I don't have to segment the string. And lastly, let's just briefly touch on maintenance schedules. When we have different types of batteries, we want to do different types of maintenance. And these are just something, this presentation will be available to you, so I'm not going to go over this in depth. Basically, this is something you're going to get. And for example, this is a VLA battery, a vented lead acid or a flooded cell. We have minimum requirements and recommended. The minimum is based upon the US NERC requirements, which are applicable to substations connected to the grid. And these are minimum required values. The recommended is what is based upon IEEE recommendations. So basically, the more reliability you want, the more you want to go toward the recommended. But you really don't want to go below the minimum. So really what you want to do is determine what your resources availability is and come up with a plan based on your resources and how critical the battery system is, somewhere in between these two. You'll notice they basically contain mostly the same tests. It is just the time frame between them that's quite different. Also, VRLA batteries, it has its recommendations here, and NiCad batteries also have their recommendations. And with that, I'm going to open it up to questions. Meredith,
Okay.
you there?
Yes,
Okay.
sorry. We have lots of questions. Okay, the first question is, can you please explain what an ampere hour of batteries is?
The ampere hour is basically how how many amps the battery would deliver in a certain hour. So if a battery has a rating of 10 amp hours, it can deliver 10 amps in an hour. So it's basically going to be the volume of current in the given amount of time.
Okay. The next one I see is, can we measure the ripple current using a normal clamp on amp meter on AC mode?
Yes, you should be able to do that. The only thing you just want to watch out for is just make sure you have the proper bandwidth on it. So you just, I'm going to be pretty honest, pretty much all of them should have the proper bandwidth. However, if you do have a lithium ion string, you want to make sure that bandwidth can get up to about 10 kilohertz. Other than that, you shouldn't have an issue with doing that.
Okay. What is float mode and boost mode? Can you please explain?
Float mode is when the battery is fully charged. So the battery is, when the battery starts charging, it's going to draw a lot of current. And then as it gets fully charged, it'll draw less current. And then finally, it will go into what's called the float mode. This is basically where the battery is fully charged and there's just a float voltage. It'll typically be on a 2-volt cell, about 2.2 volts, right in that area. And it keeps the battery topped off. A boost charge, the boost voltage, is what's used when you equalize a battery string. This is higher than the float voltage. And its purpose is that you would apply this for a given amount of time, and it helps break down the sulfation crystals within the battery that will allow you to regain some capacity of that battery. And keep in mind, please be careful when doing a boost charge that there is no rule of thumb for this. This is something you want to contact a battery manufacturer or look at your installation guide, because often the instructions are in there of exactly how to do it. Because if you keep in mind, a boost charge, you will heat the battery too, because you're at a higher level. So you don't want to do it for too long. That's why you want to follow the battery manufacturer's recommendations.
Okay, awesome. What should be the specific gravity value for a battery, and what are the routine checks?
The specific gravity is going to vary based upon the battery, the battery chemistry and the manufacturing. So really you want to look at any installation guide or in the data sheet of a flooded cell, it's going to have that information in there. That's critical information to know. Now, as far as testing the specific gravity, it's basically the specific gravity is going to be a measurement of how charged the battery is. As the battery discharges, that specific gravity drops. So you can have some batteries that have specific gravities of 1.215, some with 1.3. Again, you want to look at that data sheet. However, if you're measuring the float current in the battery and you know that battery is in float mode, specific gravity has limited applications. Where you really want to make sure that you're measuring specific gravity is when you have flooded lead antimony batteries. Those type of batteries can suffer from antimony poisoning, and the specific gravity will help you see that. But other than that, if you have a lead calcium battery, really, as long as you're monitoring float current, you don't have to necessarily do specific gravity readings.
Okay, let's see if we can get through a couple more. During operation of nickel cadmium batteries, can we infer something through impedance testing?
That's a really good question. Yes, you can, but it cannot be your only methodology of testing. Now, a NiCad battery, because of its chemistry, has a completely different discharge profile. Its voltage and impedance will remain pretty well solid until near end of capacity, at which time the voltage drops off very quickly and the impedance goes up very high. Now, with that said, so in standard testing, NiCads do and must have a discharge test done on them periodically, a quarter of their lifespan. That is an absolute requirement with them. Now, in between there, though, before you do the discharge testing, there's several tests you want to do, and one of them is measuring the straps. And most battery impedance testers, these straps will also measure the cells. And you do have something you can gain from that. One is, as I'm going through the string measuring NiCad batteries with an impedance tester, if I see some that are much higher, are real high than the others, that's a flag already that that cell has a problem, okay? But if I see they're all pretty close to each other, it doesn't mean that they're good. You still have to do the discharge test. Now, with that said, I have one caveat to offer there too, is that as NiCad batteries sit in a sit out, the electrolyte can suffer from carbonation. This is where the CO2 from the air gets into them. At that point, that will be seen as a rise in impedance. So if you may actually see a rise in impedance happening like that, where if you don't see it jump up real high, but you just see it slowly going up over time, that is a sign of carbonation. And that's where you want to take a look. You want to actually take, if you see that happening, you want to take a chemical sample, get a sample rather of your electrolyte and send it out for chemical analysis. And then you may end up finding you have to replace the electrolyte in it.
Okay. I think we're out of time, but thank you so much, Andy, for presenting today. For anyone that we didn't get to your question, we'll make sure you get an answer after this. And if you'd like a free copy of our battery testing guide, just head over to us.megger.com/getbook and make sure you use the reference code BAT-webinar. And that's it. Thank you so much for attending. We hope to see you at our next webinar.
Thank you. Thank you, everyone.